You turn on the bathroom faucet. You're trying to wash your face before bed. You hold your hand under the stream waiting for it to warm up. 5 seconds, 10 seconds, 20 seconds. It's still freezing. You start counting. 30 seconds, 45. A full minute later, the water finally goes from cold to lukewarm to actually hot. You finish in 15 seconds and shut it off. So here's the question nobody really stops to ask. What was that machine doing for an entire minute? The water heater was sitting in the basement, full of hot water, ready to go. The pipes are right there in the wall. Why did it take so long? And why does it happen every single time, even when you used hot water in that exact same sink an hour ago? The answer involves a 1860s English house painter, a Norwegian immigrant working for George Westinghouse, and roughly 12,000 gallons of water that the average American household pours down the drain every year, just standing there waiting. Here's the first thing most people get wrong. They think the wait is because the water heater is heating the water. They picture the tank kicking on, flames or coils warming up, slowly bringing cold water up to temperature, and then sending it through the pipes. That feels intuitive. It just happens to be wrong. The water heater isn't doing anything during your wait. The water in the tank is already hot. It has been hot for hours, sitting there at 120 degrees Fahrenheit, waiting for you. The problem isn't that the water needs to be heated. The problem is that the hot water isn't where you are. It's at the other end of the house. Between the water heater in your basement or utility closet and the faucet in your bathroom, there's a pipe. Maybe 30 feet of pipe, maybe 80 feet depending on the layout. And that pipe is full of water that used to be hot hours ago, the last time someone used the faucet, but has and it's cooled down to room temperature. When you turn the handle, the only thing that happens is that water in the pipe starts moving. The cold water at your end comes out of the faucet first. The hot water that's coming from the tank has to push everything in the pipe ahead of it before it can reach you. You're not waiting for water to heat up. You're waiting for an entire column of cold water to drain out of your wall. The numbers are remarkable. A typical 3/4-inch hot water pipe holds about 0.03 gallons per foot of length. A 1/2-inch pipe holds about 0.01 gallons per foot. So if your bathroom is 50 feet of pipe run away from your water heater, there are roughly 1.5 gallons of cold water sitting between you and the hot water. At a low-flow faucet running at 1 gallon per minute, that's a 90-second wait. Modern faucets and shower heads have gotten more efficient. They use less water per minute, which means it takes longer to push the same volume of cold water out of the same pipe. The plumbing in most American homes was sized in an era when shower heads ran at 3.5 gallons per minute. Today's shower heads run at 2.5. Today's bathroom faucets run at 1.5 or even 1.2. The pipes haven't changed. The fixtures have. So the wait has gotten longer, not shorter. Quick favor before we keep going. If you've ever wondered about the engineering hiding inside the systems you use without thinking, hit that subscribe button. We dig into the small everyday mysteries that turn out to have big stories behind them. Now back to the wait. This problem isn't trivial. The average American household wastes somewhere between 5,000 and 12,000 gallons of water per year just standing at the faucet waiting for hot water to arrive. That water is paid for, treated, pumped to your house, and then sent straight down the drain without ever being used. Then there's the energy cost on the other end. Once you finish using the hot water and turn off the tap, the hot water you pulled into the pipes just sits there. It cools off in the wall over the next few hours, losing all the energy that was put into heating it. Heat the water, push it through the pipes, drain most of it down the sink, lose the rest to the drywall. Repeat tomorrow. The whole system is, at a fundamental level, a slow-motion energy leak. Now here's the history almost nobody knows. For most of human existence, there was no waiting for hot water because there was no hot water on tap. If you wanted a bath, you boiled water on a stove and carried it. The first real attempt to change that came in 1868 in London. An English decorative painter named Benjamin Waddy Maughan filed a patent for a device he called the geyser, named after the hot springs in Iceland. It was a copper tank with gas burners underneath that heated water as it flowed up through pipes into a bathtub. It was the first water heater that didn't rely on burning solid fuel like wood or coal. It was also genuinely dangerous. Mons' design had no chimney or flue, so combustion gases vented directly into the bathroom. People occasionally suffocated. Sometimes the units exploded. The British still call water heaters geysers in casual speech, more than 150 years later. Mons' design caught the attention of a Norwegian mechanical engineer named Edwin Roode, who had emigrated to the United States and was working for George Westinghouse's fuel gas and manufacturing company in Pittsburgh. In 1889, Roode designed and patented the first automatic storage water heater, a cast-iron tank with gas burners underneath, a thermostat that turned the gas on and off as the water temperature dropped, and a pressure relief valve so the tank wouldn't explode. He spun off his own company a few years later. Roode Manufacturing still exists today, more than 130 years later, and is the oldest water heater manufacturer in America. The first electric tankless water heater, the kind that heats water on demand without storing it, was invented in 1929 by a German company called Stiebel Eltron. Tankless became popular in Europe and Asia, where homes are smaller and energy is expensive. In America, the storage tank won out. Almost every house built in the United States between 1950 and 2000 has a 40 or 50-gallon storage tank somewhere in the basement or garage, sitting there 24 hours a day, keeping water hot for the moment you need it. That's the hidden cost most people never think about. Your water heater isn't running just when you're taking a shower. It's running every minute of every day, all year long, fighting heat loss through the tank walls, fighting cooling pipes that drain heat into the floor and the walls. According to the U.S. Department of Energy, water heating accounts for roughly 17 to 18% of total household energy use. It's the second largest energy expense in the average home, after heating and cooling the house itself. The average household spends between $400 and $600 a year just to heat water. So engineers have been trying to fix the weight for nearly a century. The most common solution is something called a recirculation pump. It's a small electric pump that continuously, or on a timer, pushes hot water through a loop of pipes connecting the water heater to the farthest fixture and back. Hot water is always sitting in the pipes, ready to go the instant you turn the tap. No wasted gallons. The downside is that you're now burning energy 24 hours a day to keep that water moving and hot, which can offset some or all of the savings. A more recent solution is the on-demand recirculation pump. Instead of running constantly, it activates only when you press a button, or when a sensor detects you've entered the bathroom. It pushes a quick burst of hot water through the pipes seconds before you need it. The cold water in the pipe gets shunted back into the cold water line instead of going down the drain. No water wasted, almost no weight. The other modern solution is the tankless heater itself, a small unit often mounted on a wall that heats water only as it flows through. There's no storage tank to keep warm, no standby heat loss. Some models can be installed at the point of use, like under a sink, eliminating the long pipe run problem entirely. The downside is upfront cost. A tankless system runs 2 to 3 times more than a traditional storage tank to install. Here's the part that should genuinely surprise you. You've been living surrounded by versions of the same waiting for the fluid to arrive problem your whole life without realizing it. Your espresso machine. The first shot is always slightly cooler than the second one because the water and the group head haven't reached steady-state temperature yet. Coffee shops solve this by running a purge through the head before the first drink. Your car in winter. The block heater that some diesel owners plug in overnight is solving the same problem. Cold fluid in long passages. Your dishwasher. Most models start by drawing whatever water is in the supply line, which is often cold. The owner's manual on most dishwashers tells you to run the kitchen faucet first until hot water arrives, so the dishwasher doesn't start cleaning with cold water. District heating systems, the kind used in dense European cities and some American university campuses. Hot water is pumped through underground pipes from a central boiler to dozens or hundreds of buildings. Engine. Spend serious effort on insulation and circulation pumps to make sure that water arrives still hot at the far end of the loop, even after traveling miles. Hospital plumbing systems. Hot water has to arrive almost instantly at every sink for hand-washing compliance. Hospitals run continuous recirculation loops at every floor. They've solved your bathroom faucet problem at industrial scale. Hotel hot water. The reason your hotel shower is hot in 5 seconds isn't because the hotel has better water heaters. It's because the hotel runs a continuous recirculation loop through the entire building, 24 hours a day, every day. They've decided the energy cost is worth not having angry guests. Every one of these systems is dealing with the same fundamental problem. Fluids take time to travel through pipes. Time the user has to wait for. Energy or water that gets wasted in the gap. Now, for the honest trade-off, fixing the wait costs something. A recirculation pump uses electricity continuously, often 50 to 100 watts, which over a year adds up to real money on the energy bill. A tankless system has high upfront installation costs and may need a larger gas line or a higher amperage electrical circuit. Pipe insulation helps but only slows the cooling, doesn't eliminate it. And in older houses with finished walls and ceilings, retrofitting better plumbing is expensive enough that most homeowners just live with the weight. There's also a public health dimension that engineers genuinely worry about. Water that sits in pipes for long periods at lukewarm temperatures between roughly 70 and 110 degrees Fahrenheit is a comfortable environment for Legionella bacteria, the cause of Legionnaire's disease. Recirculation systems have to keep water hot enough throughout the loop to prevent bacterial growth, but not so hot that it scalds someone at the tap. The standard answer is keeping the hot water tank at 140 degrees and using a mixing valve at the fixture to bring it down to a safe temperature. That's a balancing act between energy efficiency, scalding risk, and bacterial safety that every plumbing code in the world has been quietly solving for decades. So here's where you land. That minute you spent standing at the bathroom faucet wasn't a malfunction. It was you waiting for an entire pipe full of forgotten water to clear out of your wall. The hot water was there the whole time. It just had to push through everything else first. You've been participating in a 150-year-old engineering problem every time you wash your hands, a problem that started with a Pittsburgh inventor designing a cast-iron tank with a thermostat. A problem that has been incrementally solved by recirculation loops, tankless heaters, smaller pipes, on-demand pumps, and better insulation. A problem that's still costing the average American household 12,000 gallons of water and hundreds of dollars in energy every single year. That low rumble you hear from the basement isn't waste. It's a 130-year-old appliance still doing its job, still keeping water hot for the moment you need it, still patiently waiting for you to open the tap. If you think hot water is weirder than it looks, wait until we get into why your shower suddenly turns scalding hot the moment somebody flushes a toilet in the next room. Because the reason isn't that the cold water is going somewhere. It's that 100 years of plumbing engineering has been quietly fighting a battle with basic fluid dynamics, and you're standing naked in the middle of it every morning,